Now try to generalize the ANOVA ideas to the case where we have multiple factors. So in this case, I will have two factors. So you can see that I have a first factor, it's a catalyst. It has 3 levels. Second factor, it's a temperature. It has 2 levels. And then I have the outcome, the response, right? So if we, for example, consider only one factor, only first factor, we have only 3 populations in this case. But now if you look at the data, we can see that in this case, when the catalyst is A, we have 2 temperatures, 120 and 160. And apparently we can expect that the temperature can also change the average outcome. So it means that we don't have just one population for catalyst A anymore. We have 2 populations, catalyst A and process running at 120 degrees, and then process running at catalyst A and 160 degrees, right? So in this case, it means that we have 6 different populations. And this is what I have written here. So this is exactly what we did before. We represent our data as coming from different populations. So for example, why we have this particular value, this one? Because it's a random number coming from this population with this average, population with this average, and then this is the random factor, right? Then why we have it here? Because it came from population with this average, population with this average, and this is the random factor. This is the uncertainty. And we still assume that all the variation, the variance in all populations is the same. Now let's just extend this. So it means that all our values, we have 12 values in this case, can be represented as the following sum. First of all, it's similar to what we had before, right? So it's an average effect of every catalyst level. So here we have average effect of catalyst A, average effect of catalyst B, and average outcome of catalyst C, right? Then after that, we can also think about the temperature. So it means that we have also average effect from each temperature. Temperature at 120 degrees and temperature at 160 degrees, right? So let's check if this is correct. For example, if we take this one, right? This one is this, and it came from the case where we have catalyst B and the temperature 160 degrees. And that's exactly what we have here. So catalyst B and mu2, it's a temperature at 160 degrees, right? So now we have 2 sources of systematic variation. We have systematic variation, possible systematic variation, because we have factor 1, and then we have also systematic variation caused by presence of factor 2. Then finally we have residuals, and the same idea. So residuals are fully random. So we can describe residuals as a set of standardized z-scores. The values came from standardized distribution, and then the noise, right? So the variance of our populations. Okay. So this is the theoretical representation. Now we can make empirical representation using again the same approach, right? So first of all, we compute average value response values for every level of factor 1. So average of this, and average of this. And that gives us estimated systematic variance 1. Then we compute average values for every equal temperature level. So it means that we take these values, and these values, and compute the average of these 6 values. This gives us the average 1. And then we replace all these values in the matrix with simply average 1. Then we do the same here. So we take this, and this everywhere, all runs, all outcomes where we use temperature 160 degrees, compute one average value for these 6 outcomes, and then we use this average value here. And then finally we have residuals. So what is this one, E1? It's this, minus this, and then minus this. Right? And then similarly, we have variance of the systematic source 1, we have variance for the systematic source 2, and then we have residuals, the variance for residuals. Okay. What it means? It means that now we can compute 2 F values. The first F value will tell us how strong this effect is. The second F value will tell us how strong the second effect is. And then we can use F-test, F-distribution for these 2 F values, and then find out how actually reproducible the effects are. Okay. So in this case, let me just show you an example. So we have, this is the data. So first of all, I compute the total average and subtract the total average, similar to what I have done in my examples with animals, for example, right? So in this case, I got unbiased values, and then I can compute the means, right? So for example, this is the mean outcome where I have the catalyst A, catalyst B, catalyst C. So these are the mean outcomes. You can see that it seems like catalyst B gives you the highest outcome here, right? And this is the average outcome where the temperature was 120 degrees. And this is average outcome where the temperature was 160 degrees. If you just look at these numbers, at the observed numbers, at the observed effects, you can see that it seems like both temperature and catalyst have an effect, right? So temperature increasing temperature, increasing the outcome, and also it seems like catalyst B has the highest outcome. But let's test it using the ANOVA. So first of all, you remember we split our data into sum of three terms in this case. The first term consists of these means. So these are the means. We got the mean outcome, the mean response value we got using different catalyst levels. So this is systematic 1. Then we have also these means, the matrix with these means. This is the means that we got using 2 different temperatures. So this is systematic 2. And then the residuals, right? So this is just the difference between the original value minus this mean, and that gives us the residuals, right? These are residuals. Let's check the residuals. For example, how we got 1.1. We take minus 2.1 minus 1.1, right? You remember minus gives us plus, so it means we have minus 1 here. Then minus 1 minus 2.1. So it's like minus 1 plus 2.1. That gives us 1 plus 1.1, exactly what we have here. We can check it the other way around. For example, if we take this plus this plus this, we should have this one, right? Let's check it. Minus 1.1 plus 2.1, it's just plus 1, right? And then plus 1 minus 1.5, it gives us minus 0.5, and that's exactly what we see here. Okay, so this works. Okay. Now we can compute the sum of squared values. Take every value from this matrix, square every value, take a sum. This is the sum of squared values here. Then we can compute sum of squared values here the same way. You can see that this one is much smaller actually, right? And then you can also compute the sum of squared residuals. Okay, this is even smaller. Now we define degrees of freedom. You remember that in the beginning we have 12 values, so we have 12 degrees of freedom, and then we unbiased, so we compute average and lost 1 degree of freedom. So here we have 11. Now we have 2 here because we have 3 groups, but you remember that these 3 groups, they are not independent. If you take this plus this plus this, you will get 0. So it means that every third value depends on the previous 2, so it means you have 2 degrees of freedom. Likewise here, these 2 values, they are not independent. They depend on each other because they sum up to 0. That's the effect that we subtracted the average value. So we have 1 degree of freedom. And then 11 minus 2 minus 1, what is rest is 8 degrees of freedom for residuals. Okay. Now we compute the variances by simply dividing these 2 values, right? So this one will be even easy. And then we make a test, right? So we can compute the F value and so on. So let me show you the results of this test. So this is what I did in R. So you can see that again, I constructed a long vector with 12 values that I have in the original values, right? Then I made a grouped vector 1, G1. I made a grouped vector 2, G2. And then this is how to run the two-way ANOVA. It's called two-way. When you have 2 factors, it's two-way ANOVA. You simply say the factor 1 plus factor 2. Okay. And this is the summary. Let's check the summary. Look, here I have 2 degrees of freedom. This is the sum of squared values, and this is the mean squares. This is exactly what I have here. 1 degree of freedom, sum of squared values, and the mean squares. It's a bit different because I believe that I lost some precision by using different roundings, right? And then you can see that residuals, degrees of freedom, residuals, and then mean squares, again, very similar to what we have here. Then we can compute an F value for both, and then we can compute the P value. Then you can see both P values are very, very small. So it means that it seems like very unlikely we observe the effect that we have just by chance. So it means that we can conclude that both temperature and catalyst have an effect on the outcome, right? So these are the F values, just to compare And this is the manual calculations of the p-values. You can see that I have very similar results to what I got from R. Okay. So this is how it works. And then you can apply ANOVA for any number of factors and for any number of levels. The only thing that you should care is that all factors are independent. So there is no confounding among factors. Otherwise, ANOVA will not work correctly. And then the second thing is that you have enough degrees of freedom. You remember that every time you test one factor, you lose some degrees of freedom. For example, if you have 3 levels, you lose 2 degrees of freedom. If you have 2 levels, you lose 1 degree of freedom. And then you need to have at least 3 degrees of freedom here. Well, strictly speaking, at least 1, but if you want to have a good power, you need at least 3 degrees of freedom for residuals in order to be able to see the small effects. Okay. So this is a two-way ANOVA or n-way ANOVA if you think about any number of factors. And in the next video, we will talk about how to check the quality of your ANOVA model, how to validate your ANOVA model.